Welcome to our in-depth training session on the OSPF, Open Shortest Path First Protocol. Today, we're diving into the core principles of OSPF, exploring how it operates, different types of LSAs, OSPF areas, metrics, timers, and much more. By the end of this video, you'll have a solid understanding of how OSPF keeps complex networks running efficiently. So let's get started. In OSPF, Open Shortest Path First, bandwidth is a crucial metric used to determine the cost of a link. OSPF translates link bandwidth into a cost metric, which helps routers calculate the shortest path to a destination. By default, OSPF assigns the cost based on the formula. Cost equal reference bandwidth divided by link bandwidth. The reference bandwidth is set to 100 Mbps by default in many OSPF implementations, meaning that a 100 Mbps link has a cost of 1. For higher bandwidths, such as 1 Gbps, the default cost would also be 1, which doesn't adequately differentiate faster links from slower ones. To address this limitation, administrators often adjust the reference bandwidth using the command autocost reference bandwidth. For example, setting a reference bandwidth to 1000 Mbps would allow OSPF to better distinguish between high-speed links like 1 Gbps and 10 Gbps links, resulting in more efficient path calculations. Manual cost adjustments can also be made on individual interfaces to prioritize specific links for traffic flow. Engineers can apply OSPF cost metric directly to the interface on the Layer 3 device. This fine-tuning of OSPF costs enables administrators to optimize path selection, especially in high-capacity networks, ensuring that OSPF routes traffic through the most efficient paths. Types of LSAs. OSPF uses different types of LSAs to communicate route and topology information. Here's a breakdown. Type 1, Router LSA. Each router within an area generates this LSA, which includes its directly connected links, IP addresses, and router ID. Type 2, Network LSA. Designated routers, DRs on broadcast and NBMA networks generate this LSA, summarizing the routers connected to that network. Type 3, Summary. LSA. These LSAs are generated by area border routers, ABRs, to share information between OSPF areas, summarizing routes from one area to another. Type 4, ASBR Summary. LSA, used to advertise an autonomous system boundary router, ASBR, to other areas, letting other areas know about routes to external destinations. Type 5, External LSA, generated by ASBRs. Type 5 LSAs carry routes to external networks that are outside the OSPF AS, allowing redistribution from other routing protocols. Type 7, NSSA External LSA, used specifically in not-so-stubby areas, SAs, to advertise external routes without Type 5 LSAs. Each LSA type has a unique purpose in mapping and maintaining the OSPF network structure and route information. OSPF area types and route filtering. OSPF is organized into areas, each with a specific purpose and function to optimize route distribution and filter routes. Here's how the main area types work. Backbone area, Area 0. This is the central hub of the OSPF network, connecting all other areas and carrying inter-area routing information. Every other area must connect to Area 0 directly or through virtual links. Stub area. A stub area blocks external routes, Type 5 LSAs, to reduce the size of the routing table, relying on a default route for external traffic. Totally stubby area extends the concept of a stub area by filtering out inter-area routes as well as external routes, leaving only intra-area and default routes in the routing table. Not-so-stubby area, NSA, allows external routes within a stub area by permitting Type 7 LSAs instead of Type 5 LSAs. It's often used for areas with limited connections to external networks. By structuring OSPF into these areas, we reduce routing table size, control traffic patterns, and optimize network performance. Timers. Some critical timers in OSPF include Hello Timer controls how often OSPF hello packets are sent. Default is typically 10 seconds for Ethernet links. Dead Timer determines the time OSPF waits for a hello message from a neighbor before declaring it unreachable, defaulting to 4 times the hello interval. OSPF delay and hold timers control how quickly the SPF algorithm runs after detecting network changes, affecting convergence time. Properly tuning these timers is crucial for balancing performance and stability in an OSPF network. OSPF route types and routing selection. Routes in OSPF are classified as intra-area routes O, routes within the same area. Inter-area route OA, routes between different areas within the OSPF-AS. External Type 1 E1, external routes with costs that increase based on the path within the OSPF-AS. External Type 2 E2, external routes with a fixed cost that doesn't change regardless of the internal path. OSPF uses these routes to build a complete routing table by preferring intra-area routes over inter-area and external routes. The shortest path first SPF algorithm calculates the best route to each destination, ensuring the most efficient path is chosen. Multiple OSPF processes. A single router can run multiple OSPF processes, each with its own configuration and routing table. This is helpful when connecting different OSPF domains or managing separate routing policies within the same router. However, routes aren't shared directly between processes, so redistribution is needed to transfer routes between OSPF processes or other protocols. Route redistribution between OSPF and other protocols. Route redistribution allows OSPF to interact with other routing protocols, such as BGP or EIGRP. By redistributing routes into OSPF, they can be advertised across the network. Administrators control which routes are redistributed and adjust metrics to manage path selection. It's essential to carefully manage redistribution to avoid routing loops and ensure accurate routing information. Neighbor communication and loss of hello replies. In OSPF, routers maintain neighbor relationships by exchanging hello packets at intervals set by the hello timer. If a router does not receive a hello packet from a neighbor within the dead timer duration, it assumes the neighbor is down. This causes the router to remove the neighbor from its database, triggering an SPF recalculation to reroute traffic.